Dear students, very good morning. Welcome to my course Electronic Devices and Circuits. This is Dr. Y. Pandurangaya, Associate Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering. And today's our topic is a low frequency small signal model of the field effect transistor. So after completion of this session, the students will be able to draw the low frequency small signal model of the junction field effect transistors, and also they will know that on how to use this small signal model in their amplifier analysis. Okay, and let us move on to that. What are the small signal model of an FET? In previous sessions where we learned it is an JFET parameters from the drain and as well as the transfer characteristics curves, where there are the three parameters of JFET parameters. One is the drain resistance, and the other parameter of the JFET is transconductance, and the third parameter of the JFET parameter is the amplification factor. So these are the three parameters of the JFET which we can calculate from the characteristics of JFET. There are the two kinds of JFET characteristics. One it is the drain characteristics, the other one it is the transfer characteristics. Where the drain characteristics is a graph between VDS versus ID, by keeping the VGS is equal to constant, whereas the transfer characteristics is a graph between VGS versus ID by keeping the VDS is equal to constant, where the drain resistance, which we denote with small rd, and which is calculated from the drain characteristics, and it is the ratio of change in VDS to change in ID by keeping VGS is equal to constant, which is calculated from the drain characteristics of an FET. The other one it is the transconductance, which is denoted with the GM, which is calculated from the transfer characteristics of JFET, and which is the ratio of change in ID to change in VGS by keeping VDS is equal to constant. This is called as the transconductance. Whereas the amplification factor is defined as the ratios of the voltages, and which is the change in VDS to change in VGS by keeping it is an ID equal to constant. So these are the three FET parameters of JFET, and these three parameters we can use in the small signal model of an FET. So here, if you look at those the drain current is a function of two voltages, which are the VGS and as well as the VDS voltage. So as the VDS changes, ID changes. As VGS is also changes, ID changes. Therefore, I can write it is the change in ID is the function of both the VGS and VDS. Therefore, I can write like this: change in ID by using the Taylor series. I can represent like this. So delta ID by delta VGS, and again I am multiplying with the delta VGS by keeping VDS is equal to constant, and again it is a summation of the change in ID due to the change in VDS, and again multiplying with the delta VDS by keeping VGS is equal to constant. This way of representing where the drain current ID is the function of both the gate source voltage and as well as the drain source voltage, and I am representing by using this equation or expression, which is, you can call it is an Taylor series. So by using the Taylor series, I can represent the change in current is the function of both VGS and VDS with this the equation. Or in this the equations, if I look at it, this delta ID divided by delta VGS, I can write it is delta ID divided by delta VGS. See here, this is I can write is GM I can write. So delta ID is equal to, I can write the GM into delta VGS plus ID divided by the VDS. And this I can write it is an 1 divided by RD with respect to that the FET parameters into delta VDS. So R I can write it is an ID is equal to, in simplify, GM VGS plus 1 divided by RD into VDS. So I can write that the drain current in terms of the FET parameters by this equation. This equation looks like the current equal to the summation of the two currents. Right? Once again repeat. So where the drain current in case of field effect transistors is the function of both the voltages of gate source voltage and the drain source voltage. By using the Taylor series, and we can represent that the change in ID equal to like this. Our ID equal to, I can write it is an GM VGS plus 1 divided by RD into VDS, where this equation represents that the current is equal to the summation of the currents. Usually we know that when we know that in a circuit, we can apply it as an KCL at any node. Therefore, we can write it as an equation. Or this equation represents like it is a KCL equation. So where ID equal to the current entering at any particular node equal to the currents are leaving. Therefore, I can apply it as an KCL, Kirchhoff's the current law, in reverse direction to get that what is a circuit diagram to represent this equation. So I will take it as an this equation ID equal to GM VGS plus 1 by RD into VDS. I will apply it as an KCL, Kirchhoff's current law, in reverse direction. So to apply the Kirchhoff current law in reverse direction, ID equal to, I will take it as an the drain current ID equal to GM into VGS, which represents that the GM is nothing but the transconductance, which is nothing but ID divided by VGS. Therefore, VGS maybe it represents it is a current source. So ID equal to, I will take it is an two branches where the GM VGS represents it is a current source, that I will represent like this. This is an GM VGS, right? And the other one it is 1 by RD into VDS, means it represents that it is a current across a resistance called it is an RD, and the voltage across this RD is nothing but the VDS. So if I take like this, the current flowing through this RD is nothing but voltage divided by the resistance, VDS divided by RD. So this is an one current and this is an other current, where if I apply it is an the KCL here, ID equal to what is the current flowing through this RD and what is this the current source. So current source is equal to GM VGS. The current flowing through this the drain resistance is equal to, I can write the VDS divided by RD. So this circuit is the equivalent circuit which represents that this equation, and this is ID is nothing but it is an output current or the drain current, or if I take this is a drain, output terminal is an the drain. So it is a source common for both the input and output. So this circuit represents that the output circuit, the small signal output circuit of a field effect transistor in common source configuration. Let us take it is on the input for common source configuration. For common source configuration, source is common and the drain is output terminal and the gate is the input terminal. We take it as an N-channel JFET. So where the source is the common and the drain is an output terminal and the gate is an input terminal. So therefore, I drawn it is an what is an its output equivalent to small signal model. So the input side the VGS. Usually in case of the if it is field effect transistors, we will apply that the voltage across the gate terminals always to make that the PN junctions to operate under reverse bias conditions. Reverse bias conditions we are applying is nothing but which offers a large resistance, or in ideal case a reverse bias PN junction offers infinity resistance. So infinity resistance is nothing but it is an open circuited. Therefore, if I take the gate and as well as the source at the input terminals, where at the input side it is an open. So therefore, I can check that this is a VGS voltage, the input voltage, where that it is an open means it is a reverse bias which offers the input impedance is infinity or it is an very large. So if I add this input circuit to this output circuit, and which gives that what is it's a small signal model of the field effect transistor. So all together, by combining the entire thing together, I can redraw and it will be called as the small signal low frequency model of field effect transistor. So if you look at this here, this equation is redrawn by applying the Kirchhoff's currents law in reverse direction, and we got it is this is an input side and this is an output side, where this is the VDS. So this is called as a low frequency small signal model of FET, where here the input is an open loop circuit, which it indicates that it is offering an infinite resistance or a very large resistance which is an open, where the output side it is a drain current. That drain current is represented as the sum of, like, it is a current source of GMVGS, and also it is a current flowing through that the drain resistance of RT. So this small signal model is used in case of field effect transistor amplifiers of all the cases of it is common source or common gate or common drain amplifiers, to do that the AC analysis of calculating what is its input impedance or output impedance or current gain or voltage gain. So this is a small signal model of JFET amplifier at low frequencies. So where the RD is represents as a drain resistance, GM is represents as a transconductance, where at the output side, the field effect transistor, if you see that clearly, it represents as a Norton's output circuit with a dependent current generator whose magnitude is proportional to gate source voltage. And here the GM is the transconductance, that the proportionality factor, whereas the RD is an output resistance, and the input resistance between the gate and source is infinite, since here where we are operating at the PN junctions under reverse bias conditions, right? So this is about the small signal model of field effect transistor at low frequencies. So to summarize, where that the small signal model of FET is drawn or derived by using that the FET parameters. There are the three FET parameters are there. One it is an drain resistance, other one is transconductance, other one it is an amplification factors. By using these three parameters, where in case of field effect transistors, the drain current is a function of both the VGS and as well as the VDS voltages. By using the Taylor series, where we can represent that the drain current equation in terms of the VGS and VDS by using this equation, and this equation is represents that it is an equation in terms of the currents, and which could be obtained by applying the Kirchhoff's current law to a particular circuit. Therefore, we can apply this Kirchhoff's current law in reverse direction to obtain what is then the small signal model of an FET at the output circuit, output loop. So therefore, we got it is an output circuit. Whereas in case of the FETs, the input is the gate and source, where we can operate that by applying the voltages always the PN junctions to under reverse bias conditions. A reverse bias junction PN junction offers a large resistance or the infinite resistance in ideal case. Therefore, it is an open loop at the input side between the gate and source. By combining those, the input and as well as the output circuit, and we can obtain that the small signal model of JFET. Okay, in the next session, and we'll discuss about by using this small signal low frequency model of an FET in case of FET amplifiers, and how to do the analysis of the calculating parameters of the input impedance, output impedance, current gain and voltage gain parameters. Thank you very much, and we'll meet again in the next sessions of FET amplifiers. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.